Okay, I will open up with some arithmetic just to get my mind focused. And that's done. And now to get on with the real stuff, which is looking at Paul's notes and polynomials. Okay, expand this out. And let's get on with it. Dividing polynomials. So we're going to use long division to divide this initial quartic by this linear x plus 2. And let's go for it. So we'll write 3x to the 4 plus 0x cubed minus 5x squared plus 0x plus 3. And x plus 2 right there. Then, how many x's can fit into 3x plus 3x to the 4? The answer is 3x cubed. Then multiply, so we get 3. Oh yeah, because this is so fiddly, I actually need to use a fine brush. So I get 3x to the 4 plus 6x cubed, and that has to be taken away. And we get minus 6x cubed, and bring the minus 5x squared down. Now x into minus 6x cubed, the answer is minus 6x squared. And multiply, and subtract, and bring it down. Just there like that. And then x is into 7x squared. The answer is 7x. And multiply. And subtract. And bring everything down. I say bring everything down. That's technically what's actually happening. But it would just be a lot of wasted handwriting doing that. And then x, how many x's go into negative 14x? The answer is negative 14. And multiply. And subtract. And so we get a remainder of 31. A remainder of 31. So this means that 3x to the 4 minus 5x squared plus 3 divided by x plus 2 is 3x cubed minus 6x squared plus 7x minus 14 plus 31 over x plus 2. Officially. And we'll check. Next up, we have to divide this cubic by this linear. Let's go. So first, just write it out. So x cubed plus 2x squared minus 3x plus 4, and the bar over the top, and x minus 7 on the left, and x is into x cubed, that would be x squared. Multiply, and subtract, and bring it down. X is into 9x squared, that would be 9x. And multiply, and subtract. So that'd be negative 3x plus 63x, which is 60x, and bring it down. X is into 60x, well, that would be 60. And multiply, and subtract. And so we get this quadratic here, x squared add 9x add 60, with a remainder of 424, which is understood to be divided to yet to be divided by x minus 7. And now we check. That's correct, and that's good. Next up, we have a quintic divided by a quadratic. I haven't done this. Let's see where the algorithm takes us. So it would be 2x to the 5 plus x to the 4 plus 0x cubed plus 0x squared minus 6x plus 9. And all of that is divided by x squared minus 3x plus 1. How many x squareds fit into 2x to the 5? The answer is 2x cubed. And multiply. And bring it and subtract. And bring it down. I don't think I actually need to, but I'm going to see what happens anyway. So how many x squared, how many of x squared fit into 7x to the 4? The answer is 7x squared. So now I'm going to multiply. I'm just following the algorithm. Don't know where it's going to take me. Don't know. So, yes. All right. So 7x squared times by that. So we get 7x to the 4 minus 21x cubed plus 7x squared. And subtract. And so we have negative 2x cubed plus 21x cubed, which is 19x cubed. 0x squared minus 7x squared is minus 7x squared, and bring down the minus 6x. X squared into 19x cubed. The answer is 19x. Now multiply. And subtract. And bring it down. x squared into 50x squared, that would be 50. And multiply. And subtract. And there's nothing to bring down. So I believe that the remainder is 125x minus 41, and that has to be divided by x squared take 3x plus 1. But I could be wrong, but I'm going to check. Everything has to be checked. Okay, that's looking good so far. And then we get this, and that's true. That's the quotient, and that's the remainder, and that's good. So that was long division, which takes a long time and exhausts your hand. And now for synthetic division. You can extend and generalize this so that you can divide by non-monic linear factors. Non-monic linear, goodness me, I always forget the terms. I really need like once and for all. A dividend is divided by a divisor, and then from that you get a quotient and a remainder. Quotient and the remainder, obviously I know that, but I always get dividend and divisor like mixed up. Maybe I could remember it like dividend is a longer word and divisor is trying to go into it. I know what a divisor is. Okay. So what I meant to say was you can extend synthetic division such that the divisor is not just a linear term and not just a linear term that is monic, with a coefficient of 1 in front of the x. But right now I don't know how to do that. I actually don't know. So I would have to think about that. So right, so what we do is we list the coefficients out like that. And synthetic division works when you're dividing by x minus r, something that looks like this. And then what you do is you pick up r and you put it right here. So that would be 9. No, wouldn't it be negative 9 in this case? Beg your pardon? All right. Now, here on the very first thing or column, there's actually like nothing to do. So that 1 just comes right down, just there like that. And then the 1 is multiplied by the negative 9. That 1 right there is multiplied by the negative 9. And the result comes here. So we're going to have negative 9 in that spot there. And then you go down and you add going down. You always add going down with the routine or algorithm. So 1 minus 9 is minus 8, like that. And then it happens again. Negative 9 is multiplied by negative 8, and the result goes right here. So we get 72. And then you go down, and you get 73. And then it happens again, and the negative 9 is multiplied by the 73 to get negative 657. And then you just go straight down. So, wait, yeah. 1 minus 657 is minus 656. So, then we have to interpret this. Now let's think. If I divide a cubic by a linear, I'm expecting a quadratic. Here I've got 4 numbers, but a quadratic only has like 3 coefficients, 3 numbers essentially. So these will be the coefficients of my quadratic. And this guy at the end is my remainder. Yeah. So the result should be 1x squared take 8x plus 73, and the remainder is negative 656. And of course, you can remove that 1 in the front. So we're going to check and make sure that we did that right. And that's exactly what we wanted, and that's good. Next up, we have this cubic, which is missing a quadratic and a linear term, and we have to divide it by x plus 2. The coefficients of this cubic are 7, 0, 0, and negative 1. And that's what you write down. 7 in front of the x cubed term, 0 in front of the x squared term, 0 in front of the x term, and negative 1 in front of the, well, it's the constant term, so it's not really in front of anything. We have to divide that by x plus 2. But wait, synthetic division only works when I'm dividing by x minus r, where r is just some number, yeah? Okay, so instead of 2 in the spot where r is, it's negative 2. So here we go. What comes down here? Just 7. Nothing to do with the first thing. Now, what goes in this spot? We're going to do negative 2 times it by 7, and that's what comes in this spot. And it'll be negative 14. And then add going straight down. So 0 add negative 14 is negative 14. And then we do negative 2 times negative 14 to get 28. And then add going down to get 28. And then we do negative 2 times 28 to get negative 56. And add going down, and we get negative 57. So, when we divide a cubic by a linear, we expect a quadratic as a result. When you divide a degree 3 by a degree 1, you expect a degree 2 as a result. And here are the coefficients of my quadratic: 7, negative 14, and 28. And here's the remainder. Here's the remainder, negative 57. So let's spell this out. The result of synthetic division is 7x squared minus 14x plus 28, and the remainder is negative 57. And we'll see if we did that right. We're going to see if we did that correct. And that's good. That's correct. Next, we're going to divide this quartic by this linear here. Notice this quartic is missing its x cubed term. So the coefficients of this quartic, this degree 4 polynomial, are 5, 0, 1, -8, and 2. So let's write those down. 5 in front of the x to the 4 term, 0 in front of the x cubed term, 1 in front of the x squared term, -8 in front of the x term, and 2, my good constant at the end. And synthetic division gives you a way of dividing by something which looks like this, a linear like this, x minus r. In this case, r is simply 4. So we're going to write 4 on the outside. We do our bar there, just like that. And now we're going to do synthetic division. So on the first column, there's nothing to do. You just go straight down and you put that 5 right there. Now, 4 times 5 gives you 20. Go straight down and add straight down. What's 0 plus 20? The answer is 20. Next, 4 times 20. The answer is 80. Go straight down and add what you get. You get 80 plus 1, which is 81. Next, 4 times 81. What do you get? 324. Go straight down and add what you get. 324 minus 8 is 316. Next, 4 times 316. What do you get? You get 1,264, and so go straight down and add them together, and you get 1,266. We divided a degree 4 by a degree 1, so we expect a degree 3 as my answer. A cubic as my answer, which has 4 coefficients. And there they are, right there. So here's the answer, spelled out. It's going to be 5x cubed plus 20x squared plus 81x plus 316. And my remainder is 1,266. And here we go. We're going to check. Everything must be checked. Everything must be checked. And that's correct, and that's good. So now we save. We must save it. Save it as dividing polynomials and proceed to the next section, which is looking at the zeros or roots of polynomials. What is a zero of a polynomial? It's a number which when you input it, when you put it in to the polynomial, it gives you back 0. For example, here's a polynomial. And if I input the number 3 into here, what do I get? I get 3 squared minus 5 times 3 plus 6, which gives me back 0. And therefore, 3 is a root or 0 of the polynomial x squared minus 5x plus 6. Okay, that's what they are. Okay, so here we go, practice problems. Problem 1. For problems 1 to 3, in fact, list all the zeros of the polynomial and give their multiplicities. Okay, so we open up with a quadratic. Can we factorize this quadratic? I think so. Put 2x in my first bracket, an x in my second bracket. That will give me the 2x squared when I multiply it out. And then I need to generate 13x using the factors of 7 somehow. So what I think you need to do is put a plus 7 here. This will give you 14x when you multiply it out. And then put a negative 1 there, and that will take away an x when you multiply it out. And when you do those two moves, you'll get 13x. There. So what? You factorized it, but does that tell me what the roots are? Or the zeros? Does it tell me what those zeros are? Well, yes, it does. Set this thing right here equal to 0 in your mind. Set it equal to 0 in your mind. Now, what does that tell us? That tells us that I'm multiplying this thing on the left by this thing on the right, and I ended up with 0 as a result. The only way that that's possible is if one of them or both of them are 0. That's the only way. That's why we factorize. And if it's the first one that's 0, then x would have to be equal to 1/2. And if it's the second factor that's 0, then x would have to be equal to -7. And how many times do each of these zeros occur? Well, just once. So they both have 1 as their multiplicity. And you see, it's been factorized. We've obtained those zeros / roots, 1/2 and -7. And the multiplicity of each of them is 1. Okay. The second one is massive. It's a degree 6 polynomial. What a nightmare. So, fortunately, we don't have to factorize it. It's already been done for us. Although almost anybody should be able to notice that all these terms here have x in common. So that's at least one initial move you could do. So the zeros are 0 itself and 3 and -1. I got 0 from just the x in front. And obviously, if you input 0 into this polynomial, you will get 0 out as a result. But how many times does this factor occur? Like, what's the power of this factor? Well, the answer is 1. So the multiplicity is 1. how many times does this factor occur? The answer is twice. And so the -1 from the factor right here, and how many times does this occur? Like, what is its exponent? The answer is 3, and so the multiply of that root is 3. So let's see the answer and see if that's right. And there you go. There are the roots, 0, 3, and -1. And there are the multiplicities of the 3 different roots, 1, 2, and 3. All right, let's try the third problem here, which is a polynomial of degree 8, which is massive. There's no way you could factorize that by yourself. Maybe. Although it would take a long time. And, well, let's see. What are the roots? Well, there's 4 of them. For this first one, we obtain -1. That's the first 0. Next, we obtain +4. That's the next 0. And here we obtain +1. So I'm going to write +1. And here we obtain -3. That's the next 0. Okay, so for this first one, it has a multiplicity of 2. This one has a multiplicity of 2. This one has a multiplicity of exactly 1. And this has a multiplicity of 3. And let's check. Mm-hmm. 2, 2, 1, and 3. Brilliant. Okay, so for problems 4 to 6, x equals r is a root of the given polynomial. And so we have to find the other 2 roots and write the polynomial in fully factored form. So what does that mean, that -2 is a root of this polynomial? That means that if you input -2, you should get 0 as a result. So let's verify that. So what's the cube of -2? That would be -8. What's -2 squared and then multiplied by -6? That would be -24. And finally, what's -2 times -16? That would be 32. So we have -8 minus 24 plus 32, which indeed equals 0. So because we know a root of the polynomial, and that root is r equals -2, we know that x plus 2 must be a factor of it. It must be a factor. But also, we know that x is a factor of this. So let's get going with it. Because x is a factor, we can just bring that out straight away. And we know that x plus 2 is a factor of that. So we just have to figure out the other factor of that quadratic, which is very much home territory. It'd just be x minus 8. So Right, how to express this then? Here's all the roots. We have -2, 0, and 8. And there it is in fully factored form, right there. Next up, we have a cubic with r equal to 4 being a root. So for this, we're going to have to divide it by x minus 4. That's the only way. And luckily, we can use synthetic division to cut down on our workload. So it's declaring that x minus 4 is a factor, and therefore I put a 4 there, not a -4. I'm going to have to put a 1, a -7, -6, and 72 there. Okay, so 1 should go right there. Then 4 times 1 is 4. Add them together, you get that. 4 times -3 is -12. Add them together, you get that. 4 times -18 is -72. Add them together, you get nothing. So we can now say that p of x is x minus 4 multiplied by x squared minus 3x minus 18. And does that factor? It does indeed. Into this. And so the roots are 4 and 6 and -3. And there it is in fully factorized form. Okay. Last one here. Okay, so we have a cubic which is not monic, whose leading coefficient is not 1, but instead 3. So anyway, let's get on with the show and let's do synthetic division. So I'm going to put a 3 there, and a 16 there, and a -33 there, and a 14 there, and 7, well, no, that's not right. Nearly caught me. Put a -7 right there. Okay, so synthetic division says, first just go down, put a 3 there, and then do 3 times -7 to get -21, and add them together to get -5. -7 times -5 is 35, and add them together to get 2, and then we get 0. Okay, so now our polynomial can be expressed as x plus 7 times 3x squared minus 5x plus 2. And we want to factorize this. So I'll put a 3x there, and then x there, and then minus a 2 from there, and add a 1 to there. And so the roots are -7, -1/3, and 2. And now we'll check both of those. Yeah, that's good. That's all solved. Uh-oh. Oh, darn it. Where did I go? Oh, wait. What? What? Oh, no. Oh, no. Autopilot mode. Real careful. There. That's better. That's good. That's good. Okay, so what was this section? Zeros and roots of polynomials. Done, but not dusted. Now, let's have a look at graphing polynomials. Graphing them. Okay, all right, it's not so bad. First, we have this cubic here. And we know that we can factor out x. And then we can factor this quadratic here. So it's going to be x minus 6 times x plus 4. And so the roots will be 0 and 6 and negative 4. And it's a cubic whose leading coefficient is 1. So it climbs from the bottom left up to the top right. Just like that. And there you go. It'll look kind of like that. Okay, so the middle will sort of look like this. There, like that, and there. And to make the graph faithful, do that there, like that. And that should be good for f of x. So instead of having y here, it should actually say f of x, because that's actually accurate. Yeah. So here we go. Problem 2. We'll check both of these after I've done them. So we have a cubic, which is usually a nightmare to factor, but fortunately they factorized it for us. So we can say that it has what roots? Well, 1. If I input 1 into there, I'm going to get 0 as a result. No, it's a negative cubic, so it's going to climb from the bottom, from the top right down to the bottom left. And oh, by the way, it will pass through -2. So there you go, like that. -2. And no, that's wrong. Darn it. Darn it. All right. Oh, it's that one which occurs twice. Something a little bit like that. So that's -2. That's 1. And that's -2 down there. And that should be good. And here we go. Yeah. Yeah. Oh, look at them showing off. They got the minimum. I can do that too, but I'm not actually requested to right now. That's fine. Now comes problem 3. We have a quartic which is factorized. The roots of it are -4, -1, and 2, and their multiplicities are 1 and 1 and 2. And so now let's see about graphing this. So positive quartic, so it'll climb from no, so it's gonna basically do the U shape, top left to top right. But how does it look? Well, it'll just touch it at 2. Yeah, something like that. So I'm going to have 16 there, -4 there, -1 there. Oh, and 2 right there. Now we have a quintic. A quintic with the following roots. -2 and 0 and 4 and their multiplicities are 2, 2, and 1. And now we graph it. That right there, and it's going to pass through 0, -2 there, and 4 there. Quintic, so it'll go from the bottom left to the top right. And how will this look? Well, it should look something like that. Hooray. And now we'll check. Okay, that's good. Oh, VASPA is good. And this here does more or less what we said it would do. Even though it doesn't look great, but you know. And that's great. Now comes the tedious task, the grueling the unenviable job of finding the zeros of these blooming polynomials. Okay. Right, so I'll have I wish there was some way to just like pause this, but I guess not. So I'll just have a drink of water and come back. Be well, be well.